We spoke about continuity in R. And we observed the following, that f from some interval I to R is continuous if and only if A, we have the limit as x goes to some number A of f of x equals to f of A, and that we mean by delta epsilon. B, any xn that goes to A implies f of xn going to f of A, and C, any xn going to A implies that the sequence fn of x goes or converges to something. And this looks like the weakest assumption, that any sequence creates convergence, but yet this is sufficient to establish continuity. They are all equivalent. In R, we had another condition, and that is if it's really the statement of condition A, if f of A minus equals to f of A plus, which is f of A. This D, you might say, that's actually already contained in part A when we are dealing with left and right-handed limits, but we just mentioned it. So what else we know? So we considered discontinuities of monotone functions. And what we observed is the following theorem. So if you're given a function f, and let's say it's from the open interval a, b to R, and this function is monotone. So that means increasing or decreasing, and in analysis you can make it looser. So, in calculus you might have called it non-decreasing, means that you can only go up or stay at the same level. That's what we call still an increasing function. If the function is constant, we can say it's increasing or decreasing. It's really both terms apply. So if a function is monotone, then f has at most countably many discontinuities. And the reason, I try to draw the reason for you. So let's say this is A, this is B, and let's say here we have point C at which we're discontinuous, and some other point D at which we're discontinuous, and we may assume the function is increasing. So if it's increasing, it's kind of like this, and at C, there was a discontinuity. And then you go on to D. At D, there was a discontinuity. Okay? So what we see is that the discontinuities of increasing functions are not too bad because f of a minus, that means the left-hand limit and the right-hand limit, you should have said c maybe, right? I used a for it. But basically a point inside of the interval, the discontinuity on the left and the the limit on the left or limit on the right always exist. So what we have here, we can see this boundary is our f of c minus, this boundary is our f of c plus. Then we can look at, so you see that the discontinuity at c creates a gap in the range, or in the codomain better said. It creates a gap where the gap is filled by at most one point. And similarly, if I look at the discontinuities at d, well, here they are. This is f d minus all the way to f d plus. And in this case, there are no points in this gap. But what's true is that, look at it, this red interval and the blue interval will always be disjoint, with the very worst case is that the boundary f of c plus touches the blue boundary f of d minus. So that means that those intervals of discontinuity corresponding to c and d are disjoint, and therefore each interval can be represented by a rational number. And we can count based on the rational numbers that are representing each interval. The rational number representing this interval could not also represent any other interval in the discontinuity. So you see why this is rather simple, why it happens. Okay? So it can only have at most countably many discontinuities. So the corollary that we can establish now and that's the corollary. So if I have f from the closed interval a, b to the closed interval c, d is monotone and onto, then f is continuous. Now why that happens? You see, let me try to explain why monotone and onto implies continuity. Right? So monotone implies that the discontinuities will create gaps. You see that? But if it creates gaps, this gap will not be filled. Since it's increasing, no other points, let's say farther than c, will ever be filling this gap. So as soon as you have one discontinuity, you are not onto. You have a missing segment here. Okay? So imagine that somewhere the curve begins here, maybe ends here. So that's my closed interval that contains this curve. Now this is monotone. It has a discontinuity. It cannot be onto. Here you have it. You understand? So without doing any work, we can verify that certain difficult functions are continuous, or at least functions that appear to be continuous. So let's consider an example of that. So recall Cantor function. Recall Cantor function which, when applied to delta, generated the range from 0 to 1. And how it worked is that f of x, so x is an element of the Cantor set, would have been the same as f applied to the tertiary representation, to base 3 representation of something of the form 2a sub n 3 to the power of n. So you remember how points of the Cantor set are represented. You break the number line from 0 to 1 into 3 parts, and you write 0 if it's in the left part, and you write 2 if it's in the right part. The middle parts are deleted. So what you know about the a sub n's, they are in this case either 0, which generates 0 for the power, for the numerator, or it's an is 1, which makes it 2, right? So what does the Cantor function do to the input? It changes it to a base 2 representation. Good. And what do we know about this map? We know that it is onto. You see, because what you do is just what representations do we have in base 2? We write either 0 or 1 and divide by 2, 2 squared, 2 thirds. So all strings of 0 1s can be generating an element of the Cantor set. Okay. So we recall this we have. So what else do we know about this function? This function is onto. That's because of this representation. Any number between 0 and 1 can be so represented. Like for example, 1 is represented as 1/2 plus 1/2 squared plus 1/2 cubed, etc. And 1 will correspond to 2 over 3. 2 plus 2 over 3 squared plus 2 over 3 cubed, etc. You understand how you can just go from here, just double this index and divide, instead of 2 to the n, divide by 3 to the n, and you have the element which is mapped to the particular x you're seeking in this interval. So f is onto. We also, I don't have time to repeat the argument, I hope you remember it from before, we spent some time on it. We know also that f of, so we know that if x is less than y, such that both x and y are elements of the Cantor set, then we know that f of x will necessarily be less than or equal to f of y, with equality if and only if they are adjacent boundary points, adjacent endpoints. With equality if and only if x is equal to some number of the form 0.2a1 all the way to 2an, and then maybe 2n minus 1, and it terminates in a 1. So you see, if I terminate in a 1, I can write 0, and then I can write 2, 2, 2, 2. Terminating in 1, what can you do is 0 and then 2, 2, 2. So this is an element of the Cantor set, and y so make sure you remember this. Y is 0.2a1 to all the way to 2an minus 1 and ending in 2. See, this ends in 1. So it's right at the edge where we begin the deleted middle thirds interval, and this is the other edge of the deleted middle thirds interval. When I apply the Cantor function, I need to switch this 1, write 0 and a bunch of 2's, that's how the function will be applied. But this is an element of the Cantor set, remember. If it ends up, if the last digit is 1 and all the other digits are proper, that means it's a left endpoint. So what it means is x and y are successive endpoints. You understand? So x and y are like this. So here was an interval. This here is x. And this is the deleted middle thirds, and y is here. And this was the deleted. You understand? So they are kindred spirits. They tried to stay together until they were separated by this interval, but they still stay at the edge of their what do you call it? Icebergs. They float away from one another. So, using this information, so I hope you remember that it's this formula. You remember its onto, and I don't want to just rehash what we covered. This we explained. So now what follows is that we can extend this function to a function over the entire interval. So we can extend f to a function g from the interval 0, 1 to 0, 1 by, we will say that g of z is equal to supremum of f of x, where x belongs to the Cantor set and x is less than or equal to y. The function is increasing, so you understand what we do. What we do is z, if it's located at a counterpoint, the supremum will actually be f of x. Okay, so notice if z is an element of the Cantor set, we will have that g of z equals to f of x. It's going to give us the same function, because the function is increasing. Okay, so what's I should say just not f of x, it makes no sense, f of z, and here nobody mentioned it's not x less than y, but x less than or equal to z. Sorry. Okay, so g of z will be equal to f of z. Why? Because if x is a smaller point in a Cantor set than z, then f of z is bigger, right? So if z is an element of the Cantor set, the supremum happens to also be the maximum, and the maximum of all the f of x, and that will be namely f of z, because the function is increasing. You see? So if I picked 1x that's smaller than z, f of x will be smaller than f of z. So then I can pick anything else. The best I can get is just if I pick f of z. So they agree on the Cantor set. On the other hand, so maybe let's say so. And the next observation is that g is also an increasing function. So it's increasing. How do I know? Well, very simply, just take w less than z, and then what do we know? We know that g of w, it's a supremum of the set f of x, such that x is less than or equal to w, Now this set where x is less than or equal to w, if I increase the range of x to z, I make the set bigger, and therefore the supremum might grow. And that last set is simply g of z. So the function is monotone, it's increasing just like f. We should also mention that because g of z agrees with f of z whenever z belongs to delta, we might as well say that g is onto. It's automatically onto because the function f on the counter set it's already onto. So if I just add more points that it can map, I don't change that property. So having observed this, I immediately know the function is continuous without any calculations whatsoever. So G is a continuous map. So no calculations, I have this function. Maybe on first glance it looks complicated, but I can figure out immediately it's continuous without doing any work. You can try imagining how it looks like. I think carotters have a rough picture of it. It looks somewhat like a step function with, there is a middle step corresponding to the 1/3. So between 1/3 and 2/3 it's constant. And there are other gaps, let's say, between 1/9 and 2/9, it's constant. So there are a bunch of steps, and then most of the steps are microscopic. Right? You can calculate, for example, what is f of 1/3, what's f of 2/3, where f is the Cantor function, and that's how you know how to draw g. Between them, g will be just constant.
Professor?
Yes?
For these, we just care that the function is eventually monotone, or?
Well, by monotone, it's always monotone. What I mean by monotone is that it's not changing behavior from, let's say, increasing and then decreasing. Okay. It's only, if I say the function is increasing, I mean something loose like, well, you can stay constant or you go up. Then you can stay constant or you go up. But you can never go down. If it's monotonically decreasing, you can stay constant or go down. But if you decided to go down, you cannot go back up. So that's what I mean by increasing, decreasing, right? In calculus, I think you call those, what I call increasing, you call it non-decreasing. That's the language they use in calculus, right? But we are a little bit looser here because it's not really important if it's just strictly increasing or almost that. So another thing that we want to consider is this problem. So question, an increasing, we know that an increasing or decreasing function has at most countably many discontinuities. What can we say about the following? Given an arbitrary countable set, which I'll call D, and D consists of the points x1, x2, x3, and so forth. So it's at most countable, can we create a monotone function that has d as its discontinuities? F such that the set of all discontinuities for F exactly equals to D. This means discontinuities of F, you understand? So there will be exercises, and it will be on exam 2, so pay attention. So the answer is yes, we can. Let's try to see how we might go about doing it. So what I'm going to do is I'm going to take each x and I'm going to associate to the x 1, 2, 3. I'm going to associate some small epsilon. So what I do is x1, x2, x3, etc. Somewhere is xn. To each of them, I will associate an epsilon sub n. And my requirement on the epsilons is that they are all positive and absolutely convergent as a series. So epsilon sub n is positive, and the infinite sum of epsilon sub n equals to some finite number. So let's say just less than infinity. So it's absolutely convergent. Okay? So if I add them up, you can think of this example. So you can think that epsilon sub n is equal to, say, 1/2 to the power of n. That will work. Right? So in that case, the sum of all of them adds up to 1. But all we care about is that the sum converges. So now we're going to define the function f from R to R as follows. F of x will be equal to the summation of epsilon sub n, where the sum goes over such n as that I guarantee that x sub n is less than or equal to xn is less than or equal to x. You understand? So I add up all the terms until I get x. All the epsilon sub n. Let me try to maybe give you a comprehension check. Right? So suppose that I decide that my x sub n are, let's make it simple, they are the natural numbers. For natural numbers, actually very, so x sub n is just simply n. Okay? And epsilon sub n, as I mentioned, is going to be 1/2 to the power of n. Okay. So what would be the function as I defined it at 0? What's the function at 0? So what the function is going to do is it's going to look at 0 and it's going to search for all the points of the form xn, which happen to be the integers that are below or equal to 0. Okay. So and it's going to add the corresponding 1/2 to the power of n for them. So how do I calculate f of 0? Well, I can draw the number line. I can see here is my 0. Here is my x1, here is my x2, here is my x3, and then they correspond to, so if I have 1, that will correspond to plus 1/2. This will correspond to plus 1/2 squared. This will correspond to plus 1/2 cubed. Make sense? So I selected an f of 0. F of 0 is this point here. And what the function tells me to do is find all the xn below or equal to 0 and add the corresponding red epsilons. So what do we get at 0? What do we add? Nothing whatsoever, because there is no point. You see, I decided that my xn are 1, 2, 3, 4, 5, etc. So there is nothing we add. So what is f of 0? F of 0, since we add nothing, by convention, that would mean 0. Okay? So the idea of the sum is that if you find nothing to add, you just write 0. Does it make sense? So now let's consider the same picture. And now I'm going to ask what's f of 1/2. What's that? What's f of 1/2? 1/2 is here. Now where do I look? I look always to the left. Do I find any points to the left? So the answer is 0. Yes? Now let's see what is f of 1.957. What is that? 1/2. If I'm here, I'm somewhere close to 2, but I only look below. So I go down, boom, I picked out only x sub 1. So the answer is 1/2, correct? What is f of 3.001?
Plus 1/4 plus 1/8.
Yeah, so it would be 1/2 plus 1/2 squared plus 1/2 cubed. You don't need to add it. The point is you understand how it's supposed to work. Okay. Now I gave you a very easy picture. You see, to find discontinuities at such discrete points as 1, 2, 3, you don't need this procedure. But this procedure is supposed to work no matter what countable set you get. You see, the xn could be q, all of the rational numbers. Can you imagine? So between any 2 points, there are going to be tons and tons of rational numbers, infinitely many. And adding them will be rather challenging. Okay? So you understand this comprehension check, so that's what this function is doing. It will add up the indices. The indices could not be necessarily in increasing order. I hope you understand it. It's just because I picked a very simple, mildly behaving sequence, xn, that I see that the powers of 1/2 are in ascending order. They could be very haphazard. Do I need to give you a comprehension check on that, or you follow?
If we do work with, for example, the rational, let's work with the rational numbers.
Right.
Would the summation change into an integral type thing?
Actually, the summation will be rather crazy. To actually perform it will be, you can only perform it to approximation, I suppose. Because you see what happens, the terms that you add eventually become very minute, all of them, right? So what if I had to simulate this function on the computer, I will try to understand how the rational numbers are listed, and I will find the biggest. Basically, I will find the sum of. Basically, I will find all the points up to some n, such that if you go beyond that n, the tail of the series, if I add, let's say, 1/2 to to the power of 100 plus 1/2 to the power of 101. All of this will be extremely tiny, ignorable. Okay. So then I will only find the first, let's say, 100 members of the sequence Q, and I find where they're distributed, and I will only estimate the sum based on that. But to find the true sum is a very monumental task if they're spread around. Okay.
So it doesn't turn into an integral.
No, it doesn't in general turn into an integral. It's very chaotic. Or it could be. It could be rather simple like this function, but it could be very chaotic. So in your assignments you see examples of more complicated functions of that form where you have to decide how it's adding a few numbers, and you have to decide if it's increasing or decreasing, what sort of function is it. Okay? So we have this operation. Do you understand how it works? If I were to change the numbers, I might have changed the indices, or just maybe x1 is here, and x2 is there, and x3 is there, and x4 and 5 are here. You see, it's spread around. I only add up the points that are below my line. Should I draw you another picture for it, or you get me? I don't know. So another example. Another example for comprehension check is, let's say that I'm just going to draw the number line. I don't want to explain how they are listed. So let's say that we have this point is, let's say, 1/2. And then the next point is 5/7. All right, somewhere over here is the number 8, and onwards. And let's say somewhere over here is -1, -2, and onwards. And those are my xn's, and I'm going to indicate, let's say, still by the powers of 1/2. So let's say I decide that this guy is going to be 1/2 to the power of 3. So that means he is x sub 3. So this guy is x sub 3. Maybe this guy here is x sub 7, which means this guy is 1/2 to the power of 7. Maybe this guy here is x to the power of 1, which means this is 1/2. And maybe this one is 1/2 to the power of 5. So this is x sub 5. And this is x sub 2, which means this guy is 1/2 to the power of 2. I'm just throwing them around, okay? So how would the function call? And I mean, really, I do not know fully. Let's say beyond that, to the left, there are no other powers. Let's say 1/2 squared, 1/2 to the 5th, and all the other terms, they are somewhere to the right. Let's just say that, okay? So that we can calculate. So no more x sub n here. Okay? If you move left, there are no more x sub n. So then let's see what happens if I select this as my x. So this, I don't even want to name it. I said this is x. What is f of x? Can you tell me? I just labeled it on a number line. How would this function calculate this x? Yes?
1 to the 2 to the second plus 1 to the 2 to the 5th.
Wonderful.
Plus 1 to 2 to the 3rd.
And if I move the cursor to 5/7, it will also, if it's exactly at x sub 7, it also adds the corresponding value. You understand? It adds, basically you draw half open ray, or sorry, half closed ray. You have the ray at x, and you select all the points below the x, and you find the corresponding xn that are there, and you add them up. If x sub n were describing a sequence of rational numbers, there would be an infinite sum no matter where you place the x, right? And it's going to be very complicated because if it's an infinite sum in between any two points, there are infinitely many rational numbers. The way they're going to be scattered, it's going to be rather crazy, right? So the powers will be scattered very roughly. Okay, so I'm erasing this comprehension check to clear the board and continue the discussion. Okay, so we have defined this function f of x, which is the sum, and then I want to verify a few things about this function. One thing, is this function increasing or decreasing or neither? So suppose x is less than y. Okay, what do we know about this function then? Then we can say that f of y is going to be the summation where n is such that xn is less than or equal to y of epsilon sub n. Now, x is a smaller point than y. So you already can imagine what's the relation between f of y and f of x, which is bigger? Based on what we drew, which do you think is bigger? F of y. And to help you verify it precisely, you can just say that this summation is the same as adding up all the epsilons until you get to x, and then adding the rest. Okay? So this sum is n such that x sub n is less than or equal to x of epsilon sub n plus the summation of all the rest of the n, and that is where x is smaller than x sub n and less than or equal to 1 of epsilon sub n. Okay? Now this sum is either 0 or it's positive, so it's bigger than that part. And what is that part? That's just the definition of f of x. So this is bigger than or equal to f of x, hence the function is increasing. Yes? You could have seen it even without me doing this, this formula. You just imagine the number line and imagine here is x and here is y. If you move farther to the right, you might grab more points since you are adding all the points to your left. So if you move to the right, you grab more points. Good? So I will change the sign of the exam perhaps, and you still have to have to verify is the function increasing, decreasing, and what sort of properties it might have. So, okay, function is increasing. One part already satisfied, so we know it's an increasing function. Now what we need to do is verify that D, the set of all those countable xn that I picked, is in fact the set of discontinuities. So next is we consider let's consider if x is a point that's not equal to any xm. So it's not one of the points that I specified. I want to verify continuity. Okay? Then I will consider what is limit from the right and what's limit from the left. Okay? So then let's say what is limit as y goes to x from the right of f of y. What is that going to be? That's going to be limit as y goes to x from the right of the following sum, which I'll try to break immediately. Look at it. Y is bigger than x. You agree? So I can use the top sum to break it. I can say that the summation is always, it's the limit of the sum where n is such that xn is less than or equal to x. So everything below x of epsilon sub n plus the summation where n is such that x sub n, here, x sub x sub n is bigger than x and less than or equal to y, epsilon sub n, right? That's our limit. Now, this limit is not affecting the sum that I have to my, you see that I have here, this sum. This is simply f of x. That's simply f of x, right? Now what happens to this sum? This sum is affected by the limit because now y is getting closer to x. So the way I imagine it is like in the Indiana Jones movie. This is y, and here is x, okay? So what's happening is that the wall y is being pushed towards x. So this wall is being pushed back, right? And I'm the sum, and I'm squeezed here between x and this y. What's going to happen to the sum? It's going to go to 0, but be very careful. It could be that between, if it's, let's say, rational numbers between x and y, there could be infinitely many terms that you add up. But the point is, eventually, let's say all the low terms are deleted. So for example, if we add up 1/2 to the power of n, eventually this, because x is not equal to any of them, y will eventually go beyond the point that represents, basically in between x and y there was 1/2 to the power 1. Eventually that point 1/2 to the power 1 is deleted. Do you see that? Right, 1/2 to the power of 1 might have been below x, or above y, or it's in between x and y. Now if it's in between x and y, x by our assumption is not one of those points that correspond to 1/2 to the power of 1. So if I move the wall, eventually it's past 1/2 to the power of 1, eventually it's past 1/2 to the power of 2, 1/2 to the power of 3, 1/2 to the power million. So then the sum is maybe starting from n equal to 1,000,001 all the way to infinity, but adding 1/2 to the power 1,000,001 onwards will give you just something that is like 1/2 to the power of million. You know, like that's a gross, that's an overestimation. You understand what I'm saying, right? So at most it's like 1/2 to the power of million, that sum. And then you go lower and it's less. So this thing, I just wave my hands because I'm lazy and I don't want to write it. I hope you see that this thing goes to 0, do you? You sure? You understand that this is not like the picture I drew where you have finite many points. This sum might always be an infinite series, but it just involves different 1/2 to different power, let's say, right? So maybe I look at the smallest 1/2, and eventually the wall eliminates it. And I look to the next smallest, eventually the wall eliminates it, and then the sum can be estimated above by the tail of an infinite series, which always goes to 0 if the series converges. So that simply is equal to f of x. F of x, right? So it is right continuous at that point, right? By the way, this will verify this is still true because look at it, xn is bigger than that, right? And this will be still true if x is equal to xm. Still true if x equals to some x sub m. Why? I don't want to, you see, so I said if x is none of them, right? If x is not the xm, and then this limit, this guy will disappear to 0, so the limit will be f of x. But now I also say that in fact, if x was one of those points, that will still be true about the right-hand limit. Because look at the sum. This sum does not involve x sub m, right? The sum is it's only summing terms that are bigger than the x and less than or equal to the y. So it doesn't matter what this point is, right? It squeezes everything in between, removes them. Do you understand that? So the conclusion that I get from this point is that f is right continuous. What I mean by that is that f of x plus always equals to f of x, no matter what x is. You get it? So I said if x is not xm, but make sure that you see that even if I said x is xm, that would not change anything at all. Really look very careful. That's what you have to look very careful, right? On the exam, I will modify this question. So look really carefully here. You have to interpret what this is doing. So now I verified it's right continuous. Let's see what happens if I consider the limit where x is not xm, but I go from the left. What happens if I go from the left? If x is not x sub m, let's consider, I'm using still, maybe I'll use z. Limit as z goes to x minus of f of z what is that going to be like? So in doing this calculation, let me consider what is f of z. So let me consider first what is f of x. It's easier to consider bigger terms. So if I look at f of x happens to be the summation where n is such that xn is less than or equal to z epsilon sub n plus, right, that's my f of x, plus the summation, and now watch it very carefully, right? This is less, so now the summation is n such that z is the smaller number, and here we have the xn, and that's less than or equal to x. Because in this case, z is smaller than x, so I break it first by z, and then between z and x. Look where we're pushing it, right? X in this case is my right wall, and I'm pushing from below. Okay? What is this guy? This guy here is f of z. So this is, so it's f of z, and this guy here, well, I'm not going to give it a name. Or maybe I should. Right? I'll give it a name, and I'll call it vz, so that I don't have to copy it. Okay, so this will be also dependent on z. This depends on z. This depends on z. So that would be v of z. So now I can look into this equation, and I can see that the limit, I can solve for f of z. What is f of z? F of z is f of x minus v of z. So to take the limit as z goes to x minus of f of z, I just need to consider f of x here minus v of z. So you see, f of x I don't need to bother with, and then here we have minus v of z. Now could you tell me what's going to be the limit for v of z?
0.
And now you have to be really careful. Do you see that x now is the right point, right? So how am I pushed? Z is here from below, and it is pushing me to the x. Where the summation here, look at it, it includes the x. It always, this x is, if it contributes an epsilon, right, it's always, the epsilon is always added to the sum because we have less than or equal. So it means if we look at this point, if this point is x sub m, we always add epsilon sub m. So in this case, notice x is not a point, so we might as well, in this case, right, v of z, I can erase this less than or equal sign. So in our case, because I assumed x is not equal to x sub n, I can say that v of z is also the same as the sum where n is such that z is less than x sub n, less than x epsilon sub n. I don't change the v of z where I delete less than or equal. Look at that very carefully. I'm claiming that this is still v of z. Why? Because x is not those points, so the last x will not contribute anything to this sum. So yes, v of z, its limit will be 0. You see, similar result. We're squeezing here everything in between. We see at no point is the sum necessarily equal to 0. It's just the sum is the tail, at most the tail of some infinite series where the beginning of that tail is very high. It's like 1/2 to the million. You understand what I do? When I push z close enough to x, I squeezed 1/2 to the power of 1, 1/2 to the power 2, 3, 4, etc. if they were inside. And therefore whatever epsilons that remain to add are all of very high index n. And therefore the sum of all epsilons of very high index n will be next to 0. That's by convergence of infinite series. Unfortunately, I didn't cover it in this class, but perhaps you remember from Calc 2. So this is f of x. So what we know already is the function is continuous everywhere where it's not d, right? So I'm erasing this part, you have it. Hence, f is continuous on the complement of d. Right? D is this set of the xn, right? So if I pick any point that's not part of D, it's continuous there. What's the complement of D? In our case, it's on R, remove D. So every point of R outside of D, we have continuity. So we already have at most countably many discontinuities, which are necessarily parts of D. Notice we observe that this function is right continuous. So now, if x equals to x sub m, what happens now? What is limit as z goes to x minus or f of z? What's going to be this limit if I did pick a point xm? I don't want to copy it, so we will go back in here. Now notice, is this equal now? No. So what I have is that this is going to be limit as z goes to x minus of f of x minus in f of x I might as well write f of x it's equal to x sub m, so it's f of x sub m, right? The function at m minus the summation where n goes, where n is such that xn is bigger than z and less than or equal to x sub m, the particular right-hand point, epsilon sub n. What's the limit now? What is this limit, please? So we clearly see that we have f of xm, it's not changed because it's not affected by z. Right? This guy is not changed, so we just need to find the limit of the guy that depends on z. So that would be f of xm. Is it done? What's the limit here?
0.
Incorrect.
Incorrect.
It's not 0. Now look at this, right? In the summation, look at the sum. I'm squeezing things out. What I'm not ever squeezing out? This, which is x sub m. Therefore, what I'm never squeezing out is epsilon sub m. So this is this minus epsilon sub m. Look at this. That's why I said pay attention here. Here I could have I deleted the less than or equal. So in other words, from the squeeze out, I can ignore x because it's not part of the sum anyhow. But I cannot do this here. Cannot be ignored. I cannot delete less than or equal because you see, it has to be, before it had to always be less than or equal. So this term potentially contributed some epsilon. Just in the first case, because x was none of those points, it did not contribute anything. But in this case, x is that point, xm. So the sum has a bunch of stuff that's squeezed out, but always epsilon sub m. So it's going to be, when you take the limit, it's going to be like the tail that vanishes to 0 of an infinite series, and still one guy that doesn't vanish ever. So that's what survives. So the function is not left continuous. At any point in D. The implication is that the set of discontinuities of F happens to be the set D. It's exactly what we were searching for. So the implication of this theorem, even though you can come up with simpler examples, is that there is a function that's continuous everywhere except on every rational number. So it's continuous everywhere, but not on any rational number. Can you imagine that? All the rational numbers they're dense in the number line. So the way this curve would look like is just you just have a very wild jumping around the rational numbers, and then you have a nice behavior on every irrational number. One example of such function, by the way, explicit, is the popcorn function. Maybe I think it's in one of the assignments, you can look at it. So if you graph it, it looks like exploding popcorn. All right, so we have a few minutes, so let's start talking about what continuity is like on abstract metric spaces. So again, pay attention to this example. Make sure that you understand how it works, because I promise there's a question like this on the exam. So what do we have in an abstract metric space? So in general, now we are dealing with a function f that takes a metric space M into the metric space N. Okay? And then how would we go about and define continuity? The natural definition for continuity will be, let's say, delta epsilon. F is continuous at some point x if what? If there is a function delta epsilon, which is a real valued function, right? Such that for epsilon bigger than 0, distance from x to y less than delta epsilon will imply that the distance on the metric n between f of x and f of y will be less than epsilon. Right? What is the geometric interpretation of continuous functions? Continuous functions don't rip fabric apart. They don't pull things apart. So that means, how do you describe it by delta epsilon, is that if things were together, they will remain together. You see, so if the point x and y were close to one another, they will remain close to one another after I take their image. You understand? So very obvious examples of continuity, let's say, is just simple rotations or rigid motions, isometry. So for example, when I take this paper and I lift it from the table and I place it like this, what is the transformation? It's the transformation from, let's say, R2 to R3. Now what happened to the point? So each point in R2 retained its distance once I lifted it to f of x and f of y, where f of x is a point in R3 and f of y is a point in R3. They retain their distance exactly. So that's if I don't change anything. But what can I do? I can take the function, doesn't have to be one-to-one, and I can actually make the distances closer, right? So I can kind of crumple the paper or staple it here, and I brought a bunch of points that were far apart, I brought them together. Still, points that are close together, if you take a point x and you draw concentric circles around this point x, in the image you will still see some sort of deformed concentric circles. That's the idea of continuity. It could be that the distance is increasing because I can stretch the piece of paper. If it's made of rubber, I can stretch it rather hard. Right? So it's not true that the points that were very, very close, they might actually be now very, very far. The point is, if I have arbitrarily close points, so here's a point x, and I drew a bunch of points, a sequence that goes to this x. When I stretch the fabric, I will still see possibly a stretch sequence, but it still goes to the point f of x. Okay, so that's the definition of continuity by delta epsilon. We try to capture this geometric notion, and now we can try to capture this this notion by sequential definition. Okay, so that's one idea how we can try to describe continuity. Another idea, sequential, is that if I trace a bunch of points that go to x, so that means if the sequence xn goes under the metric d to x, that then implies that f of xn will go under the metric rho to f of x. Okay? So the idea is I took a point in this piece of paper, and with my marker I made a bunch of dots that get arbitrarily close to that point. And if the function did not rip the space apart, I will see, no matter what the deformation, I will see that those points they still go to the point f of x. At the very worst, I collapse the entire space to a single point, in which case they are just there. You see, so the idea of continuity, you can bring things together, but you cannot pull them arbitrarily apart. We're going to learn that soon in terms of connectedness and other properties that continuous functions have. Maybe I'll state one more thing, because I guess we'll have to continue this in the next class. So we can use, the idea here, the statement here, what does it describe? It tells us that the continuous functions commute with limits. So in other words, I can say that limit as n goes to infinity of f x sub n should equal to f of the limit. Okay, so that's just really stating what's drawn on top. Now we can describe continuity by open bows. It's really the same thing. So we might say that for any epsilon, if for epsilon bigger than 0, there is a ball of radius delta centered at x, such that if I take the image of this ball at x, the ball is in the space M, what I'll get is everything will be contained in the ball of radius epsilon in the space N centered at f of x. That's capturing again that same idea, that, that if I take points that are arbitrarily nearby some point x, they will be lifted arbitrarily nearby to the point f of x. Okay? So the idea here is what I do is I take a piece of paper, I take the point x, and I draw a very small circle. If the circle, and then I take the image under the map and see what happened to the circle. So the circle might be folded and crumpled and not very good looking, but it still is going to be fully contained in a neighborhood around f of x. That's really the same as this statement. Think about it, right? If the distance between x and y is less than the delta, then the distance between f of x and f of y will be less than epsilon. So those two statements are essentially meaning the same thing. Yes? Do you see that? That they mean the same thing, because how do we measure open balls? Open balls are the collection of all elements that are within epsilon. So that's exactly what happens here. So all the elements f of x will be within the open ball because all y in this ball will be f of y less than epsilon. So they are inside. Good?